after my ramblings. I forgot to get to the right slide. Let's see. Oh yes, we were doing that, so I'll do it. Okay. So during the last time, I had a thing about a score system, a demo, so I wanted to talk about this briefly. I'm going to go just a little forward, show you what I'm talking about, and then demo it. So let's see, current slide. Okay, that hurts too. Zoom meeting. So reminder from last time, all input is evil. That's just the simplest way to think about life. It should be treated as potentially dangerous. So you should code responsibly. You should validate all inputs, use appropriate tools or functions to get the inputs, recover appropriately. What do I mean by this? Well, there are some times when you're asking for an input, it's supposed to be in a special format. Okay, there's something like which we call SQL, structured query language, used for accessing databases. And we'll show some examples of that when I talk about web security. But it has to be of the right format. And there's SQL validation tools out there to make sure it's of the right format. Those should be used. You roll your own, you may make mistakes. And if there's an error, what do? You know, like I said, you should recover responsibly, recover appropriately. So check the input. You know, is the data the right type? Is it within a range of possible values? Do the values make sense? Too long, too short? Format in a special way, date, phone number, etc. I'll show you some examples of this in a minute. There are functions, and if you're not writing code, you're not going to see this or understand this. Certain functions that are not safe. You know, so there's get string. It reads a character from standard input, that's the keyboard, and stores it in the string variable until a new line character end of line file is found. It's impossible to tell without knowing the input data in advance how many characters it'll read. If it reads too many, we get what we call a buffer overflow. There's lots of ways this can happen. Now, get character reads just one character at a time so that you can count. There are several other ways of reading inputs where you limit how many characters. You tell it, hey, I only expect 50. I'm not going to read more than 50. Read no more than 50. Okay. Those we'll talk about in detail in later classes. But even those can be wrong. So there's a whole bunch of functions that deal with strings that have problems. Okay, the reason strings have problems in languages like C or C++ is they don't have embedded with them the actual length of the string. So a programming language like Pascal or Python or others will have, when the program is storing information about the string, like my name, Jim, it'll say Jim, and Jim is 4 characters long, right? No, it'll say it's 3. Because Jim is 3. It'll say it's 3 characters long. C and C++, when they wrote it, they decided, man, we're not going to do that. That takes extra memory and extra management. What we're going to do is at the end of a string, we're going to store character 0. Now we have in the, like I've mentioned before, bits is bits, ones and zeros represent different things. We have in our programming languages, an encoding of keyboard characters, numeric characters to numbers. So space is character 32. Capital A is, I don't know, 64, something like that. I don't remember. And there's a list, there's a mapping of the standard encoding, ASCII, the American Standard Coding Information Exchange, or Computer Information Exchange. Character 0 then is never, The characters below 32, so 0 through 31, are non-printable characters. They make a bell, they do a new, say, hey, go to the new line. They're like for controlling printers and stuff, and character 0 is a null character. So they said, hey, we're gonna have character 0, you read the string, it's a non-printable thing, you get to a 0, you say, that's the end of the string. These string copying functions and string manipulation functions, they say, hey, copy from this string to this string. It says, hey, okay, I'm copying from A to B. I'm going to read this one to get to the 0 character. And those are all the things I'm going to copy. But if I don't know the length, I copy wrong. So like I said, there are some functions. There's a string copy function that just says copy everything. Another one, string n copy, that says copy up to n characters, up to 100. So I can say, hey, copy from source to destination, no more than 100 characters. Safe, right? Now, because now I'm not going to overflow the buffer. If that 100 is correct. But if I put in the wrong number, I thought it was 100 and it was really 50, I had a problem. And so people think, oh, I've got it because I'm telling it a number, it's automatically safe. No, because I have to make sure I'm telling it the right number. And there's some classic examples of where people counted wrong and that broke. So just to understand, these are some of the issues we're going to see. You should have proper messages if there's a problem. Tell them, hey, you entered too many characters. I only accept up to 50. I asked for a phone number. And, this is the other thing. I asked for your legal last name, the right characters. Drop the bad input, start again. Parse it. Parsing is when you're reading the character inputs, what they typed, and interpreting it. So you can read in phone numbers, 208-885, and know what they are. You can read the number 1234 and know that's 1,234. You can take the comma, maybe it's 1, 234, and get rid of the comma. You can make changes to the input as you're reading them. Drop certain character symbols, so you can filter it. You can truncate if the input's too long and throw away the rest. All those are possibilities. Wait a minute, let's see. Okay. So we're going to go over some of these. There are both unintentional and intentional problems in coding. Unintentional, non-malicious programming oversights. These are just mistakes programmers make, but they cause vulnerabilities in programs that attackers can take advantage of. So buffer overflow, integer overflow, incomplete mediation, off by 1 errors, format string vulnerabilities, unsafe utility programs. I'll go into these. Malicious code or malware is software that deliberately does something wrong. So yeah, I give you something that looks like it's a game. It actually acts like a game and steals your bank records. It contains a virus in it that spreads across your system. Those are things. I'm not, for secure coding, I'm not as worried about that. I'm worried about you not having mistakes in your code. So I hinted around this one little more. Memory corruption errors occur when the contents of a memory location are altered due to an explicit assignment in a way that's not expected. Now, buffer overflow is the most common type of memory corruption. It's a software bug in which data is copied to a location memory exceeds the size of the reserved destination area. When overflow is triggered, the excess data overwrites adjacent memory locations. So what do I mean by this? Hopefully you can see this. This is a piece of C code. All right, I'm going to go over this in a little detail because I know, one, a lot of you don't program in C, you may program in C++. It's similar. Some of you don't program at all. That's understandable. What I have here, let's see. Let's go here. Is a program or a function we call main. When you take a program, I should back up. When you take a piece of code like this, it's written human readable format. You send it to a compiler will translate it to machine code that's actually executed. Part of that machine code and the executable file format tells the program where to start. By default in C and C++, it starts at a function called main. So it says, let's call this and do this first. Now this piece, it's a simple if then else, if else statement. It says if check access. So if this is true, do this. Well, this says call a function called print and say access is allowed. Else, if it's not true, call access denied. That's all this does. Check access is defined above here. And in this, I have what we call the two variables. Now, a variable is just a name for a memory location. It's a way of accessing. You think about algebra. You say, oh, well, you know, I got to deal with this. I got X and Y. Or geometry, I got X, Y, and Z. Those are just names. Why do we name things? Why don't I just give it the memory address? It's easier to use a name. The compiler picks the memory address for me. I don't have to know which one it is, and it can change it around, and I don't care because I give it a name. Names give you power. If you've ever read fantasy novels and you know in magic, if you know the true name of something, you got power. That's what this is. But are these the true names? That's the question. So I realized I forgot to make this the bool. There's a library called standard bool. In C, you don't have a default of true and false values. False is 0, true is everything non-zero. Hard coding, manipulation, bad programming practice to do that. Better to use a standard, give it the names false or true. I should have called this bool, I forgot it. By default, C says, hey, we don't have Booleans. Computers don't have Booleans, we have numbers, and we'll just pick numbers to represent something and pick 0 to represent false, and everything else is true. Anyway, this is an integer. I call it allowed. And I say initially, you're not allowed, it's false. Then I set an array. So this is a list of characters. Characters are single characters, A, B, C, whatever. And I allow up to 20 of them in this array. And that's my password. So I ask them, I print out, enter your password. And then I read from the keyboard the password, and this says read it as a string from the keyboard and store it in the password here. Now this does not, I'm not using a safe one. It does not tell read no more than 20 characters. Oh, by the way, one of those 20s is this null character. So I should say read no more than 19. So I have room to store that null. And then I do a string compare function. I compare password. Well, that's not a hard password, but that's the one I'm using, to the one the user typed in. And I say if it's equal to 0, I shouldn't have done it that way. But no, string compare says if they're the same, return 0. If the first one is alphabetically less than the second one, it's a negative number. If it's alphabetically greater than the second one, turn a positive number. So you know if this string is less than, equal to, or greater than, that's where we get the number. So I say they're equal. If I've given the right password, I return true. I set allowed to true, and then I return allowed. So returning tells it go back to the calling program. So this now gets either a false or a true to say we've checked the password. If it's true, access is allowed. Hopefully that makes some sense, especially those who aren't taking programming classes yet. Yes.
And so the password, it won't be like stored. Like if you access the code, it won't be stored.
I can't hear you.
Oh, okay. So the password that they enter, it won't be stored like in the code. It will be stored like it'll be encrypted, I guess.
No encryption. This is bad coding.
Oh.
So one, the default password is hard coded into the code. This is the right one. Not encrypted, nothing. So if somebody could look at my code, they would see the real password. But this is just, I'm going to run it. I'm going to say, hey, check the password. Let's see if I can get this. Oh, come on. Okay, let's see if I can get this. Where am I? Huh, where's my Zoom session? It's not running on this one yet. Okay. There it is. Oh, all these things we got to sign in again and again and again. That's that's right, because I hadn't used this laptop in a while. I'm trying to log in with Zoom. Let me log in with Zoom. Signed in. Let's see. I just don't see me logged in. Let me try this one more time. Open Zoom. Is that working? Sign in. Single sign in. Continue. Now launch it. Oops, something went wrong. Oh, that's cool. Well, maybe this demo won't work. Let's see if I got a different way of doing this. Sorry. Let's see. How else can I do this? Oh, I could do it that way. Connecting. Are we there? That's right. It won't let me sign in twice. Okay. Finally. All of this just to get to this. Okay. So my program. I called it test one. Enter the password. If I say, Jim Boy, it'll say access denied because that's not the right password. If I say password, it says access allowed because that's the right password, right? And that was my program, right? The same one that I showed you. Okay, but I compiled it. I ran, the compiler I used was Clang. I said, hey, give me a program called test one from test1.c. So compiled it, ran it. Then when I run test one, like I said, I could do, hey, give me a password. It gets me in, good, okay. Let's try to run this again. What if I enter the password 12345678990? That's not good. What if I enter that twice? Actually, I'll enter it 3 times. Access allowed. Well, that's good. Okay. What happened?
Your array was set to 20 characters.
My array was set to 20 characters. I typed in 30. I typed in 30 characters. So I'm going to show you one other thing. I'm going to compile this with a different compiler, GCC, because I need you to see this. I'm going to call it test one also. And I'm going to run that. And I'm going to do the same thing. Hey, maybe that's faster. Stack smashing detected, terminated, aborting, core dumped. Okay, I'm going to come back to talk about that in a second.
I compiled mine with GCC and it didn't do that.
Depends on the version of GCC and what you're doing.
Oh, yeah, I guess that's true.
Did you have one with a buffer overflow?
Yeah. And it said allowed. It didn't do me this stack smashing.
Yeah, depends on the version. I'm using the latest version of GCC with some defaults in it. Okay. So what happened? What happened was in the Clang version, I wrote in 30 characters, so it overwrote these 20 and went up. And overwrote false with a non-zero value, which is true. And then when it returned allowed, which is now true, and came back here and said, oh, true, access allowed. So I did a runtime patch of the code. I modified some stuff by typing it in. Now, what happens, I'll come to. The compiler actually turns this into assembly language, which converts things into machine code. So these numbers here, 55, 48, 89, E5, that's the actual machine code that's created here at these memory addresses in the program. This is the assembly language, the lower level encoding of that. This is from the Clang version. This is Intel assembly, but I'm using what they call the AT&T format for it because it looks different depending if you're doing the Intel or AT&T. Anyway, none of that matters. I'll explain this. So what the program does, this is for the function check access. It stores RBP. I'll tell you about that in a minute. It copies RSP to RBP. I'll tell you that in a minute. It subtracts 30 from RSP, 30 hex. So it makes room for 30 hex. 30 hex is 3 times 16, which is 48. 48 bytes of data, which is actually more. I only needed 24 because an integer and, oh wait, no, this is 64-bit code. So integers are 8 bytes plus 20, I needed 28. It gave me some extra. By default, the compilers sometimes do this and put some padding. So they say, well, maybe we want access at an 8-byte boundary. So although I said give you room for 20 characters, I'm going to make it a multiple of 8. So I'm going to give you room for 24 characters. That type of thing. This tells me, okay, actually, this was a 4-byte it's using. Interesting. It stored 0. That was initializing access to false. And then it used an address and did some other things. Okay, what was happening here? We have our stack in the programming language. When we call a function, it stores the return address on the stack, pushes it on the stack, and stacks grow down, as I mentioned before. Then it did a push of RBP. RBP is what we call our stack frame pointer. And it keeps track of where we are. So everything below this is technically part of that current function. When we return from the function, we just want to make this available again. And so RBT tells us, well, where were we? And as we add new things to the stack, we keep moving the stack pointer down. Every time we push something, it goes down. If we subtract something, it goes down. So this is our current stack pointer. So if I call another function, it'll push a new return address down here and go further. When I return, it says, oh, reset the stack pointer to here. Just undo it, and then it pops this off, so stack pointer goes back up and then returns to this address, popping that off. In your functions, it stores memory for those local variables. So it stores allowed here and then the buffer below it. And because it counts down buffer location 0, we start counting at 0 in computer science. So except for Pascal, apparently the first entry in an array of Pascal is a 1, but everybody else uses 0. Buffer 0, the beginning of buffer is here on up. So RBP points here. This is where the stack pointer was when it did that copy. It said, hey, copy the current stack pointer over. So store the base pointer, move the current stack pointer into the current base pointer, and do things. So base pointer -4 puts me down here, and I can say that's the start of this allowed because everything counts up. So starting from here up, put a 0. And that's what this was doing. So that's why I know where that was. And it's -4 because it's 4 bytes down. So when I overflowed this. What GCC did and why it did me stack smashing is it switched the order of these on the stack. It put the buffer first and allowed underneath it. So if I overflowed the buffer, right above the buffer, it put a very special value we call a stack canary to randomly assign value. And then before the program returns, the function returns, it looks and says, did somebody overwrite my canary? Did somebody kill the canary in the canola mine? Canary in the canola mine? Wow. Canary in the coal mine, it detects something bad happened. And so they overrode it with the inappropriate value. It detects it, says stack smashing detected or done. Some compilers will do this, some won't. Some versions will, some won't. You can turn it off. And I'm showing you this because these things happen and we get problems. Okay. Let me try one other thing here. We'll go back to this one. I have a different program that was the one referenced. I got to use the right keyboard. It's a scoring system. Well, with a scoring system, now let's say Jim again is the student's name. 10 scores. I got 100, 100, and 100. I'll only do 3. -1 to say I'm done. I have 3 scores. Sum is 300. Average score is 100. Based on the average score, final grade is A. Yay, that looks good. Yes. Okay, that worked. Actually, let me clear this. Let's run it again. Let's have Jim Bob in there now. Jim Bob didn't show up to class. Got 4 zeros. Right? Student score scores, sum is 0, average score is 0. Based on the average score, the final grade is F. Does that look good? Yes. Student name Jim Bob, final grade F. Everybody comfortable with that? Think you should fail? Let's go back to Jim Bob. Let's see, 4 scores, give him a -1. Looks good. I'm not sure. Final grade A. Again, the same problem. I had a buffer. This one was C++ code. I had a comment I could put in that was only 5 characters long. And right above that was the grade. And so the default grade was X, and then I did things and it broke. Okay. Let me do one other thing with this one. Enter student scores, 0 to 100. If done, enter -1 to stop. Oh, they didn't do anything. -1. Floating point exception, core dumped. Why? Why do you think that might happen? I did calculations on nothing. I added up all the scores and divided by the number of scores. 0 to get an average, and divide by 0 is not a good thing. It can cause you problems. Not always. In Java, divide by 0 gives you infinity. Well, a positive number divided by 0 gives you infinity. A negative number divided by 0 gives you negative infinity. A negative, and you can have negative infinity divided by negative infinity, whatever. We did find a bug in years ago in the original Java thing where a negative number divided by negative infinity was still negative. And it was supposed to be positive, but they had made a mistake in their interpreter. So these things happen. Okay, now I'm gonna do one more. Let's show you. Let's see. I showed you the code. I want to scare you here a little. There's a tool called obj dump. It says take the object file and dump it out. PDFH gives me some examples. So in a typical program, this was the test program. It is an ELF64 file. ELF is executable linking and file format. It's the default executable format in Linux, Mac OS, Windows uses their own. It's an x86-64, so that's Intel 64. So architecture, Intel 386 up. Flags, these just tell me it has symbols, dynamically linked, dynamically paged. And here's the start address, 10E0 hex. That's where the program starts. Now, because it's dynamic, and I mentioned address space layout randomization with operating system, what it does, it takes that 10E0 and adds something to it and says, that's where we're really going to start. Program has a whole bunch of sections, headers, interpreter, loading, all these. We'll skip those. These are all the different dynamic sections and addresses it has. These are the dynamic libraries up here that it needs things from. glibc is a standard GNU version of the standard library for C. Different versions of that library used by different pieces of the code. Fine. All these different sections are in my code. The only one I was really looking at was the text section, which is where the actual executable code is that I wrote, and these are default things. So there's a lot of things in here in a default program. And then it actually disassembles and shows you all the pieces of it. Here's the default start for how it starts. These things, don't worry about, those are just default library stuff. Oh, there we go. There's a main, and I had check access right above it. So there's a lot of debugging capabilities and other things you can do. I'd love it if any of you can understand this stuff and work with it. This is where I live and breathe and work on a lot of stuff all the time. Okay. Let's go back to this. But that's where we got all this. That's where we got this thing. Click on there. There we go. Okay. So overriding, if I don't control the buffers, I can overwrite. I can overwrite other variables. These could be counters, results of computations, other things, a return address. So if I overrode high enough and there wasn't the stack smashing detection, I would change that return address. And I could redirect the control flow of the program. If the attacker fills the targeted return location with some code to do something, connecting back to the attacker, running a shell. So you saw when I was logged in, I was typing commands, that's a shell, right? So if I can cause it to run a shell for me and I can have access to the shell, I can do whatever I want. I can tell the shell to run certain programs. Okay, so in hacking, shell code is a small piece of code used as the payload, as what's delivered, as the weapon, as the explosive, the munitions, whatever, and what we're delivering in the attack that actually has it execute something interesting. Usually, or initially, it was execute a shell command. That's why they call it shell code. Now, it doesn't have to be that anymore. Okay, any piece of code performs a similar task. So what happens here is we have our buffer, our previous frame pointer, that's where I push the RBP. Return address is here. So if I can overflow that return address, if I know exactly this size and my bad input file comes in, I change the address to a new address. And if I put it, old style attack, I overwrote the address into the stack. And then I put my malicious code in on the stack. And because I knew all the addresses, everything was fixed, well-defined, I just had this return to the stack. And I said, hey, I just loaded this code, run it. That was cool. We don't allow this anymore. It used to work. It's a good example of how it works. It's an easy way to do it. How do we stop this? Stack is data, right? Stack is not code. So we said, hey, operating system developers, microprocessor developers, allow us to put the stack in a piece of memory that is not executable. It's readable, it's writable, but it's non-executable. So when you say, hey, jump to this location in the stack, the hardware says, there's no executable code here, friend. So attacker said, well, shoot, that's annoying. But I know something. I know how this works. Notice here it says arguments. These are, when I'm calling a function, I can give it some arguments. And then I call the function, it stores the return address for the function, it's other things. The function, when it's running here, actually looks at the arguments. Notice when I showed earlier, I had the -4 RBP to say go down and say, well, +4 RBP would go up. +8 would say, hey, give me argument 1. So the code knows where those arguments are. What if I overwrote the arguments? Then my return address, instead of being returning to where it should have been, I'll actually make it the start of another function. So when this quote unquote returns, all the return does is says change the location where you are in memory, run this. It says now running at this location. Oh, I'm running at the start of a function. That start of function then looks at everything else I've ever written and said, those are my arguments. So what I do is say, hey, I'm going to return to a command in the standard library and tell it, hey, run me a shell. I'm going to put in the override bin/shell and say, hey, execute this, and it'll do it for me. And so all I do is call an existing function in your program and tell it to do something for me. So there's ways they've tried to fix that. Or people say, wait a minute, I know something else. I've got your whole code. There's pieces of your code that do really interesting things for me. And they're followed by a return instruction. So if I return you to the start of this interesting piece of code, have it execute a few lines, then it'll return back to me. Then or it'll return, which means it'll go back to the stack to look at the next thing to do. And I'll give it another one. I will piece together these little, what we call gadgets, and have them put together an interesting piece of code for me to execute whatever I wanted to do. That's called return-oriented programming. You can do the same with jumps, which is jump-oriented programming. Michael Franz, a faculty member at University of California, Irvine, wrote something several years ago, which would look at your program, find all these gadgets that are useful, all these things, small bits of code that do interesting things with your registers and stack and that. And then said, okay, now I got a normal piece of code. I want to execute this as my attack code, my shell code on your program. We'll compile your shell code into a collection of these gadgets automatically for me. Give me the attack of all the return addresses I need for this to work. And so he wrote a little compiler to compile an attack script into a return-oriented programming script and did it. Why? Why make that available? Actually, he never made it publicly available, but he made the idea available, and that was enough. There's now ROP Gadget and a bunch of other tools out there which pull out all these things for you and tell you, hey, this is what you can find in your code. So modern operating systems make the stack non-executable, so hackers used attacks into libc return-oriented program. So the operating system used address space layout randomization, stack smashing techniques. So hackers used heap overflows instead of buffer overflows and other techniques to overdo that. So then operating system developers did other techniques, and then attackers found a different way to do. It's a non-ending game.
It's not just all cybersecurity.
That is all of cybersecurity. Yes, it's an arms race. Now, I have gone back over the literature. I don't remember. The last time I counted, I found like 100 different papers in conferences and journals talking about return-oriented programming techniques and ways to fix it. Oh, we are going to recompile your code differently so that if they know the gadget's in one version, it's not in this other version. Or we're going to modify our code so that they can't, these gadgets don't exist. We know the common gadgets people are using, so then they find out the gadgets. And I was actually talking to Michael Franz about this at one point. I said, you know, Michael, can't we just stop buffer overflows? Then none of your return-oriented programming works. The root cause is we are not bounding our buffers. How about we just focus on that? And he said, but I got this big grant. What was this?
How do you bound a buffer?
How do you bound a buffer? So one, you use a safer programming language in C or C++ that has default buffers, you know, that knows the size of buffers and just doesn't let you overwrite it. You use the safe programming functions. We actually, so there was a competition I mentioned earlier called the DARPA Cyber Grand Challenge. And what we were doing, we didn't get this part completely working. We were looking at the code and saying, okay, this is a place where you're copying into a buffer, whatever. We know the buffer size. We're going to just check each time you're copying, make sure you don't go past that size. As a programmer, you can do it. You just have to use the right functions, and there are tools out there that check your source code to see if you're using the same functions. But again, you have to use the right number. And this is the problem. And Michael was saying, there's too many ways for people to make mistakes. We can't trust the developers to do it right. You know, I think I gave this example before, but I'll give it again. So I was at a conference, a security conference in the early 2000s, probably 2004, 2005 timeframe, and somebody from Microsoft was talking about a recent buffer overflow they had problem. And he says, so this was after we shut down everything at Microsoft and put everybody through extensive training. Bill Gates was serious. We are not going to have any more security vulnerabilities in our software. We did months of training of everybody. We have new programming standards, new ways of doing things. We went back and looked through all our code for all these problems. And there was a publicized buffer overflow. So I, who was in charge of security of this product line, got called into Bill Gates' office. As I go in and Bill Gates says, so we're here to talk about this whatever attack. First thing I need to know is who wrote this code and why is he still working for me? And the guy says, it's not his fault. He said, no, we did all this training, it's his fault. He goes, no, it's not his fault. What they did is their standard technique was now in every function that passed a buffer, the next argument would be the size of the buffer. And you would use that in doing your checks. Well, in standard Microsoft good coding practice, they didn't hard code in values. They used defines. They used a define is like an alias, a nickname for something. So pound define size 100. Every word place you see the word size in your code, the compiler replaces it with 100. Macros is another term for them. The problem is, as you saw in the C code, we have includes. What includes say is find this file, standard bool.h, string.h, and load it into the program. These are our header files. This is where we define the macros. This is where we define a bunch of other things. They're standard ones you need. I have to load standard.h to know what printf really is. String.h to do any string compare. Standard bool to get false, etc. I can have my own. What if I define, so like pound, this is pound sign, so pound define size 100 in one of these files, and pound define size 100 or size 50 in another file. I defined it twice, what happens? Well, it should detect that. Problem is, I have the ability, when I'm compiling things, to say, I could take main and put it in a different file. I could compile this and create a binary, an ELF file, object, what we call an .o file, an object file, that later I can combine with the one from main to make one program. So I can compile lots of different files separately and then merge them together because, hey, who wants a million lines of code in one file? Well, they had their default function that this guy was writing, including certain things that define size. The other place that actually created the buffer was in a different file with a different header that defined size a different size. And so it defined it and created it a size 100. But then up here, he thought it was a size 128 because they had two different header values of the same value from different headers, and just the way you compiled the code, it wasn't compatible with itself. When the guy tested it, he tested it all using his own header, but when he sent it to the actual build system, it didn't check and it built it with the wrong header for the thing he was linking to. So these type of problems happen, and that's why we can't solve it. That's a long explanation, but it's like, yeah, interoperability gets to be a problem. When you have large groups of people working on the same thing, you have problems. You have conversion problems. We lost a probe to Mars because, oops, one group was using meters, one was using feet. So it was estimating how many feet above the surface it was instead of meters. So it crashed. The other, can I do this one? I think I can type something. Do I equals 1, 3 is Fortran code. It says loop, starting with I, start at 1, then do 2, then do 3. And so you do this code 3 times. What if I made a mistake? What if instead of a, oops, how do I undo this? I'm on the wrong editor. Let's see. Sure, it's not gonna let me do that. There we go, erase this. What if I type 1.3? That's a decimal number. By default, the 4chan compiler just assumed that meant 1. It rounded down and only did the thing once. It didn't do it 3 times. We lost a space probe to Venus because of that in the 60s or 70s, maybe. Okay. So, let me make sure I'm doing all the right thing. Okay, I still got something going on here. There it is. Okay. Talking about numbers, in coding, we have several different numeric data types. In C and C++, I talked about some of these before. We have some default sizes. A short integer is 2 bytes in size, 16 bits. The value is from negative 32,768 to 32,767. Unsigned short integer, no negative, so we go from 0 to 65,535. Unsigned integer, default 4, up to 4 billion, or signed from negative 2 billion to 2 billion. Long integer, same thing. Unsigned long int, 0 to 4, same thing. Long int is 64 bits. I'm not going to show you what that is. That's too many. But it's 8 characters. Unsigned long, etc. There it is. Assigned character is negative 128 to 127. Unsigned character 0 to 255. This just gives you some examples. Int by default, I have here is 4. This is not quite correct. Depends on the machine. If I'm on a 32-bit machine, it's 4 bytes. If I'm a 64-bit machine, it's 8 bytes. There's some default types we're starting to use and see more commonly, like int 32, int 64, uint for unsigned int 32, uint 64, so you know exactly what size you're doing if it matters. It may not matter to you. So unsigned integer values range from 0 to the maximum that depends on the size of the type. Maximum value can be calculated as 2 to the n minus 1, where n is the number of bits used. So a 4-bit signed integer, if we had 4 bits, nobody does 4 bits anymore. It's 0 to the 2 to the 4th minus 1, or 0 to the 15th. 8-bit integer, 1 character, 0 to 2 to the 8th minus 1, or 0 to 255. We use a representation called 2's complement, but it's unsigned integer representation. It's just in 4 bits, you know, all 4 zeros is a 0, 3 zeros and a 1 is a 1, 0, 0, 1, 0 is a 2, etc. Signed integers are used to represent negative values. On a computer using 2's complement arithmetic, signed integer ranges from negative 2 to the n minus 1 through 2 to the n minus 1 minus 1. Okay. How you actually get a negative number? You find the positive version of it. Say it's a 2. You flip all the bits, so you get 1101, and then you add a 1 to it. And 1101 plus 1 is 1110. And that's negative 2. The reason for that is if I add this number, binary, and this number together, 0 and 0 is a 0, 1 and 1 is a 0, carry the 1, which puts it here. So 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. Oh, that's too big. So I throw that extra 1 away, and I have 4 zeros left. And so 2 plus negative 2 is 0. That's cool. Means I don't have to implement subtraction hardware in my machine. I can just do addition. And I add 2's complement negative numbers to 2's complement positive numbers, and I get the right answer. And if I added a -1 to a 2, or let's say a -3 to a 2, it would actually end up as -1. I'd have all ones. Because this 1 and this 0 would give me a 1. This 1 and 0 would give me a 1. This 1 and 0 would give me a 1. This 1 and 0 would give me a 1. I'd get 1, 1, 1, 1. So it's pretty cool. Which means the computer doesn't know it's supposed to be a negative number or not. The computer has no idea if you're using unsigned integers and that is really a 14 added to a 2, or if it's a -2 added to a 2. Let's actually look at 2 plus -1. That's an easier one. So all ones and zeros. So the 1 and 0 is a 1. The 1, 1 would be a 0, carry the 1, and we'd have a bunch of zeros left over. So we'd get a 1. 2 and 15 would also give me a 1. With a carry, an overflow of a 1, it's actually supposed to be 16 plus 1. That 5th bit, but it's not there. We don't have it. Depends if your system's set up to detect that. Hardware usually isn't. No, you gotta, actually it is. We flag that you have an overflow, and then we let your program decide if you want to care about it or not. But the hardware just says, hey, I'm gonna just add things together. If I want to compare things, is A greater than B? What does the hardware do? It takes the B, converts it to its 2's complement representation, so it becomes a negative, adds the 2 numbers together. It becomes now A minus B, or A plus -B. If it's positive, we know A was greater than B. If it's 0, we know they're equal. If it's negative, we know A was less than B. And so the result of the comparison function will be positive, 0, or negative. And we can have a way in the hardware to detect that. So the hardware, a comparison is really a subtraction function. But we don't do subtraction, so it's really convert to 2's complement, then add. So, like I say here, 2's complement maximum and minimum. Our maximum value is all 1s, our minimum is all 0s, 8-bit unsigned, 8-bit signed. Our maximum is actually 127. Our minimum is -128. And all 1s is -1. All 1s is not 255. All 0s, well, that's 0. Notice there's one extra. This is one, that's 128 negative numbers and only 127 positive numbers. Why? Why aren't there 128 of each? I have 0 to 255 here. That's 256 numbers. Why do I only have?
0.
Because 0 counts. 0 counts as a non-negative. So we have 128 negatives and 128 non-negatives. Some systems like to have a -0, just even it out now. So our ranges, assigned character can be here, unsigned character is here. Short would be here, unsigned short is here, we're short 16 bits. Notice that there's not complete overlaps. There is an overlap here of unsigned short to unsigned character, or from short to both unsigned character and signed character. Those are fine. I can easily convert this to this. But converting this one to this one gets to be a problem, from signed to unsigned. So their basic integer types in C and other languages have a minimum maximum possible values determined by their underlying representation in memory. Simple arithmetic on a variable such as addition, subtraction, multiplication can result in a value that can't be held in that variable. Right? So, if I'm just using basic decimal and say, hey, I've got 4 digits instead of 4 bits, but 4 digits. Well, I've got 4 digits, but I need 5 to represent the value. That's an integer overflow. It is too big to be represented. It is higher than the maximum possible representation. What happens when what could go wrong when that happens?
You get a negative number.
You could get a negative number. Because it could overflow if you're in a signed representation. If I'm from -128, yeah, let's go back. What is 127 plus 1? That's, I add 1 to this, it propagates all the way up. I get 1000000. I go to -128. If I did not detect that, if my software doesn't care, adding 1 to 127 suddenly lost me 120 or 256 numbers. Not good. I mentioned the conversions, the type conversions. If I'm trying to compare a signed and unsigned, it just automatically assumes this is signed. And all it does is just interprets it as signed. It doesn't change the negatives to anything. Just, oh, no, this is actually positive 128. I can cause myself buffer overflows if I'm doing my math wrong. I'm calculating the maximum size of this buffer, but I did the math wrong. I'm trying to see, am I going to overflow the buffer? And is it bigger than my maximum? Well, my maximum happened to be 127. That was the buffer size. I said, okay, I'm combining these two strings together. Are they too big? Well, length of A, 100, length of B, 100, add them together. Oh, that's -73. That's not bigger than 127. I'm good. Does that make sense? I see a shaking head. So if I'm using an 8-bit representation for the size of my buffer, and I'm using signed numbers, and I add those two 8-bits together, I got a problem because my math is wrong. And this has happened. We've seen this in code where people add things together. They get a really large number. They add it, it overflows, becomes a negative number. They're comparing it to a number to see if it's too big, and it's not too big. Common way of doing this is if I can send a data packet to you on a network, or I can type a value or give you some other value and say, hey, this is the buffer size I want you to process. This is the size of everything I'm giving you. And you do a calculation on it, then check. If I give you like the maximum possible integer value first, and then you add something to it. Because like one thing is I know people say, oh, this is my max size of string. Say, oh, I'll add 1 to it to make space for that null character. And then I'll see if it's too big. Well, I give you the maximum possible integer, you add 1 to it, it's now very negative. And so it's not too big, and I'm good. So we see these problems in code as people are not thinking how these numbers are being represented or what's being used. Half the time because, well, nobody's going to, if I'm using a 32-bit value, nobody's going to send me a 4 billion byte buffer. So I'm not going to worry about it being above 4 billion. If I can convince it is, I win. So these are the types of things you have to think about in secure coding. There are several others, actually, that we go over in the class. I'll go back. That actually I realized I'm not going to talk about here because it's just too much. But an off by 1 error is a common one. If a buffer, I'm looking at things, and so I have my buffer size 20, right? But it's from 0 to 19. If I loop from 0 to 19, not 0 to 20. And often programmers miss by that 1. And they'll put in, oh, is it less than or equal to 20? No, it's less than 20. Especially when they're calculating lengths and stuff. Or you forget about that null character at the end. It's 1 character longer than you think. This can cause problems when you can overflow one thing, and that could be enough. And usually that's not detected by a lot of the tools because you're not stacking the smash. Wow. I'll be so glad for break. When you're not smashing the stack, but you're doing something else. Incomplete mediation when you're not checking everything. I'm not doing a full check on the buffer, not doing a full check on the input. Format string vulnerability, I'm going to show you that one later with the web stuff, because that gets some interesting stuff. Unsafe utility programs. Yeah. So how do we deal with this? This is the important part. How do I make sure I write good code? How do I make sure the code I'm shipping is good? And that's dealing with code auditing. The binaries, how are they actually even created? So we have our bunch of C code. We have our header files. We have our C preprocessor that says, hey, for each of these C codes, grab the header file, put it all together. So I can now see, merge it into pretend one file, then send it to the compiler. The compiler reads this one file and everything in it, and then creates assembly. And then that assembly, that's that percent RBP or whatever, is then created into an object file, an executable file, not an executable file, a binary file. Those are then linked together along with other standard libraries to create your executable. The default is a.out in C, unless you do a -o and tell it its name. That's the standard process of the compilation process. Now, we could have programs which are interpreters. An interpreter doesn't compile to an executable. It takes what you're typing or what you've typed or from a file and says, read it and figure out what to do right then and there. Does that make sense? So it's not creating an executable. There's nothing else. When I'm on a shell and I'm typing commands like ls and it lists the file, that's an interpreter interpreting what I'm telling it to do. BASIC was written with an interpreter. Python is an interpreter. Several other things are interpreters. A lot of the web-based stuff is interpreters because you download the standard code from the website, JavaScript or whatever, it's in human readable format. Now, some machines will take that and do what they call just-in-time compilation. Well, I've got it now. I'm going to compile it as I've loaded it. My browser is going to take this code. I just download this from the web. I could keep reinterpreting it every time I'm executing, or I can compile it, create a mini executable for it and run that. Usually what they do is they create a mini portion of the executable somewhere in the heap, the dynamic memory, call that and run that. Oh, great. Attackers now have a new place to attack. So where do we need to look and deal with security? Everywhere. I need to make sure these libraries are secure and they're used correctly. I need to make sure these headers and C files are put together correctly. Somebody needs to make sure this compiler and assembler do the right thing. That's not your job. So what do we do when we want to look at code? One thing we can do is what's called a code audit. And this is something people can do even if they don't know programming as much. The auditing process is a pre-assessment, an application review, a documentation and analysis. Okay, now it could involve looking at the actual code. This is, what is this? MSLS handle application. Just who knows what it is. A sample of code. The pre-assessment is done by the management team or the auditors. What is the goal of your assessment of your code? What is the goal of the audit? Are you just trying to catch the easy to find vulnerabilities? Maybe. Maybe your focus is going to be on specific security related modules, authentication, encryption. Maybe you're going to do a complete review. What do you have access to? What do you look? Do you have just the source code? You can look at the source code, something like this, but you can't run it. Maybe you only have the executable. Okay, if I only have the executable, how do I test it? Well, I can run the program. I can try things. I can say, hey, here's a piece of code. What can I do with it? You know, first thing I'm going to do is I'm going to enter 1,000 A's and just see what happens. I'm going to pound it. I'm going to just see if there's mistakes. This is something a programmer doesn't have to do. It could just be anybody doing. Just, are there things wrong? I could have the source in binary, so I can look at the source code and test portions of it when executing. I can have what we call a check build, so binary with a lot of debug information gives me more information about it. Or it could be a true black box. Hey, I was talking to somebody at Hewlett Packard who was really mad about this one time. So he was in the testing division, and the thing they did at Hewlett Packard is basically the developers developed code for, say, a printer, and then they handed it to the testing division to test it. So he shows up one morning, there's a note on his desk and a disk. This was a long time ago. Here's my software for the new XXXY printer. Please check it. I'm going on vacation for 2 weeks. Nothing else. That was it. No documentation, no source code, no anything. Says it was one of the hardest things he had to check. But he had a deadline. They had a deadline to get it done. Developer didn't give him everything he needed. If I'm downloading software from the internet, I don't know. I might have an idea what it does, but I have no access to anything. Or maybe there's the software is running on a server somewhere. I don't even have access to the binary. I just have the interface. And I want to do an assessment on it. So I have a web interface and I can send it requests and get responses. I have, software on an embedded device. I can interact with it some way. So pre-assessment is trying to figure out just what are you going to do? What are you going to test? How are you going to test? What are you going to try and find? What is the goal? And then importantly in this, how are you going to report the results and what is the meaning of the results? How much time do you have? Some code is harder than others. Why? Why would some code be harder than others?
It's newer language.
Complex.
Well, okay, 3 of you at once. That was cool.
Coding language.
It could be the language used.
Like the nuance of the language, if it's like brand new or
Say that last part again.
like if it's a well-known language or not.
So again, if a well-known language, yeah. Have you programmed in D or F sharp? Right.
Well, it could be a more complex program.
More complex program.
If you're looking at Windows, if you're looking at Word,
Yeah.
different.
I'm looking at cryptography versus a simple hello world program. I'm looking, there's a huge bunch of difference. We need to collect information about the program. I'm doing an audit. I need to collect information. I can interview the developers, ask them about it, explain the code to me. Look at their documentation. Developers are often horrible at writing documentation. Horrible at making sure the documentation is consistent with what they actually coded. Standards that have to be followed. If I'm doing a payment card industry standard, there's the payment card industry digital security standards, or PCI DSS. Are you following that? If you're doing other network protocols, are you following those, et cetera? So we collect all those. Those are things I can test against. I can do a design review. This is useful for prioritizing and scoping. What did they put in their document? How do they design the code? What does it look like? Well, did they even design the code? Is there a design document? Is it up to date? Maybe a third party is involved who doesn't want to share the documents. I use this code I got from this other person. Their libraries, I don't have their design documents, so it would be a problem. Other developers may not be available. If I want to do a review and I want to interview the developers to get the design documents, they may not be available. Why may they not be available to me when I'm being hired by the company to do a code audit?
They don't work there anymore.
They don't work there anymore. That's a very common one. Or they're on vacation, or they're on a different project. And sometimes it's like, okay, we need to do an audit of this. Bill worked on this last year. Hey, Bill, you're in for the interview. I don't remember what I did. That was 3 projects ago. Clients may not want to pay for design review. I want you to find the vulnerabilities in my code. Why are you looking at the design? The design's not what's executable. Just find me the bugs. Actually, I'll stop there. So there's several other things we do when we talk about application review process. Avoid drowning. We'll avoid drowning after Thanksgiving. Any questions, comments, concerns? All right. Have a great break. If you're going anywhere, just drive safe, fly safe, whatever, because there will be icy roads probably somewhere out there at some point.